let us have a go at problem 2. The first thing is that we should find the type directly. I don't really know what he means by that, but in section 8 on page 41, some examples were given where the type was found. So I expect that finding the type directly means copying the method of page 41. That was one point. The next is that checking how many points have order 3 and 4. And so I wanted to prepare that. We have the points of order 2, of course. The points of order 3 are given by this equation, or these x values, and there should be a plus minus in there, so that we have 4 x values at most, or possibly 4, and then for each we might have none or 2 points. Order 4, I wanted to prepare that, so I did that work. And I'll just show, so we have to check whether square root 2 or square root minus 1 lies in the finite field. And to find whether the square root lies in the field, we use the Jacobi symbol. I did that without really knowing whether one could do that, but we'll come back to that later. So first I will show one example of this computation. So I started with a curve. N does not need to be 1 here. And then we have the points of order exact 2. And the point of order 4, twice that point needs to be one of those. So let's assume that 2 times xy equals minus n point naught. And one way to do that is to say that the slope of this line must be equal to the slope of the curve here, of the elliptic curve. That means that y divided by x plus n equals the derivative. We call this f of x divided by 2y. Multiplying by 2y, you get y squared divided by x plus 1 equals the derivative. So the derivative minus this guy, and that's very easy because we can factor out x plus n here. So it's x times x minus n. And then a factor 2. So we get 3x squared minus 2x squared minus n squared plus, and then plus 2xn minus n squared. We have a discriminant 4n squared plus 4n squared. That's 2 times a perfect square. So for order to have a point ending up, the x value requires square root 2 to be in the field. So that's the first condition we get here. The second coordinate has to be there as well, so we compute f of, and then we have to find the solution. I'll just find it up here. So that became a multiplication sign divided by 2. 2 cancels. N times minus 1 plus minus square root 2. And we write this as x times x minus n squared. Oh, it's get into the third from the in there as well. This guy squared gives 1 plus 2, that's 3, plus minus 2 square root 2, and then n squared, that gives minus 1. Now wasn't it plus minus? Yes, it was. And this is 2 times minus 1 plus square root 2. So it becomes 2n times n squared minus 1 plus minus square root 2. So this is a perfect square. Thus the square root of 2n needs to lie in the field. Square root 2 already must lie in the field. So that gives us square root n as well. So going through that point, we need to have only square root 2 lying in there. Then we'll have 4 points. So that's a yes. Now if square root 1 lies in there, then the other ones will work as well. So that's how I got this table. So this is exact order 3 and exact order 4. While up here I have the unit element included, so that's not exact order, obviously. Well, then we are ready to go. Prime 3. That's by the proposition of numbers. Now I don't know which number that is, I'll just find it. It's also some way back. Yeah, that's proposition 16, which tells us that we have q plus 1. So the the elliptic curve we just call S. So this, I'll use that as a general notation. The order of S is 4, and it contains the unit, of course, and then the 4 points of order 2. So that must have type 2.2 to have 4 points of order 2. That's the first one where we need to compute the number of points, and I'll do that by hand, and then I'll do it in Mabel, so I can, it'll probably be difficult with some of the other primes, so I'll be using Mabel for that. We have plus minus 1 are not interesting. Plus minus 2, that's the only interesting point. I'll just take plus minus 1 with as well, though. And then naught, of course, but we don't do that. X squared, 1 minus 1. X squared minus n squared. So then f of x, that's the product of x and this. So that's naught. And minus 2 minus plus 2. And then we need to check. That's not quite right. 2 times 2 gives 4. That's minus 1. So it's actually plus minus 1. And they are both square. So we have the unit, points of order 2. That's 4 points. And then we have 4 points down here. 2, and then the square root of, that's 1, and the square root of minus 1, that's 2. What am I doing now? Minus 2. And minus 2.1. And then it's of course plus minus always. So 1, 2, 3, 4, 5, 6, 7, 8 points. I was about to say that obviously it must be of type 2.4. If it was cyclic, then we would only have 2 elements of order 2, unity and p to the 4, and the generator to the 4th. And if it's 2.2.2, then we would have 8 points of order 4. So that's a general principle that a prime only occurs twice, because the number of orders of a prime is less than or equal to p squared, the prime squared, because of the denominator in the expression for the sum of points. Lies way back. All right, P5. So maybe we should do that in Mabel as well. I'll come back to this later. So we need to test for each element in f whether or not f of x is a square. Let's make a sequence. It's much better. And we need to find the squares as well. There's the squares. Actually, we should go up to p minus 1 here. So we see we hit squares all the time. And maybe I should exclude unity and p minus 1. It's good to have them. So 1 point, 2 points, 2 points, and 1 point. That's 6. And then we have naught as well. So let's take naught in as well. So we add 1, 2, 3. That's our 4 points, of course. And then 2 and 2, that gives 8. So 8 points by proposition 16 again. So it must be type 2.4. 11. S equals 12, which is 2 squared times 3. So the type must be 2.2.3. So, how many points do we have when the prime is 13? One, 3, 4, 9, 10, 12. No, no, no. 1, no, no, 2, no, no, no. 4 points, that wasn't many. Three and 10 are the only guys. So it's 8 points altogether. I claim 2.4 again. $17. You know what? I should do this a little more brilliantly. So and we'll test it with 13. We define the set of squares in F13, and then if f of x lies in that set, print and we want x as well as the one here, just for making sure. That verifies what we already saw with 13. Let's do 17. Oh yes, of course I didn't take the trivial one node with in the set of squares. We just have to count 1, 2, 3, 4, 5, 6. That's 12 points, and then the 4 of order 2, that's 16. And when we only have 4 points, it must be 2.8, the type. That means we have 2 points of order 4. 4 of order 4. I will verify that. We have to check whether 2 and minus 1 is a square. And we could see that in Mabel, 2 is a square and 16 is a square. That means that we should have... Oh, that's just possible. It's of type 16. It can't be. Then we've only got 2 points of order 2. If it's just the cyclic group of order 16. But then we would have. We take this guy. Let's say the generator is A, then A to the second, A to the fourth, A to the sixth, this guy has order 2, so it can be multiplied with the generator in here to get the 4 of order 2, and then these 2 have order 4. And they can be multiplied by, if you multiply that guy by that one, so we multiply it by one of these, by this one or not, to give 8 altogether. But I claim when both of these roots exist that we have that we have 12 points of exact order 4, and I can only see 8 a to the second power and a to. Why don't we use additive notation? So I write 2a and 4a and 6a. If we call the element here of order 2 for b, then we have a to the second, a squared b, a to the fourth, a4 b. This should be 6, of course. Why doesn't this give us 6 points of order 4? Let's go on. This is mysterious. The next prime is 19. There we have 20 elements. The type must be 2.5. And p equals 23. So here we have 24 elements. It is 2 to the third times 3. My mind is still wandering up to p equals 17. I believe here it has to be 2.4.3. Oops, I've been writing the type in the wrong way. It's 2.2 squared traditionally, etc. This way we should have 4 points only of order 4, exact order 4. Like we had up here, a squared, a to the sixth, and then the same times b. next time I do this, I will try to use the additive notation. I think it's too late to change it now. The question was whether square root 2 and minus 1 lies in the field, so we have to compute the Jacob, or that's the Legendre symbol, and that's minus 1 and 2 times p, or 2 over p. We have to see whether it's plus minus 1 modulo 8. That is exactly what it is. It's 3 times 8 minus 1. So that means we should have 4 points of exact order 4. Right. That was the first part, 8 primes. I'm still in doubt about number 17, p equals 17. Could it be 4, 4? I will write it the right way. That would give us 4 elements of exact order 2 and 16 elements of order 4. That must be it. Simple. I just didn't see it. Yeah, I need a break now and then we'll carry on. I've had lunch, ready to go again. 9:27. Oops. So that's 1 modulo 4, so we don't know the number of elements. We'll have to figure it out. And now what exactly are we going to do? First we are going to make a list of all the squares. What's wrong here? Use f in squares equals sequence of... Oh yes, that was silly. That wasn't many. 1, 2, 3, 4, 5 squares. That's of course what we must have. Silly. Silly me. Well, I'll just leave it for the time being. And then for x, if x to the third minus x squares, then print x. Let's do the guy as well. Use fn if x to the third n squares, then print x and x to the third and x. Let's see if this was the problem. It wasn't. Let's see if it was the third. Use fn. For x in f, do if so that can be done. Oh yeah, 3, that's not a good choice. I thought this was plus t. It doesn't do anything. So it's just minus 2. Oh no, n squares. So we get the same list as before. That was silly. Then we should have an eval b. So we can print x. It doesn't like to put it in the third. Oh, it did. Then what about minus x? Bang! So maybe it doesn't like to subtract. So let's, this is minus 1. That works. That really was weird. So x to the third minus x. Naught should give naught. 1 should give naught. 2 should give naught. That's strange. Oh, it does. So that was, I'll print the result as well, since I cannot read it very well. There we go. So, the 3 point on the axis, horizontal axis, and then 1, 2, 3, 4, 5, 6, that's 12 points plus 4, so we have 16 points altogether. That's 2 to the 4th. This gives a number of possibilities. 2 to the 3rd, 2 to the 2nd, 2 to the 2nd. Here we have 4 of order 4, and here we have, I'll just write them up. So the generator here is A, the generator B. So we have A, A squared, B squared, and B squared. Don't be ridiculous. So A and B have order 4, and then they can be multiplied to each other. So that's the 12 of exact order 4. And then they can be, yeah, that's it. Now, what am I doing here? That's like only 3, but then they can be multiplied by A squared or B squared or both, giving altogether 12. So we need to know whether we have 4 or 12 of exact order 4. So we check whether 2 or minus 1 lie. The square root of 2 or minus 1, that's the same. So one of them must, because we have elements of order 4, and then they both do. So without performing any computations, I can say that this is the answer. Right, 27. There we have 28 points. So it must be 2 squared 0.7, the type. All right. Next, 71. That's a prime. And 72 is a multiplum of 4. So we have 72 elements. And that equals 2 to the third times 3 to the second. 8 times 9. So number 2, the 2 must be 2.4. And then we have 2 possibilities. One is 3 squared, and the other one is 3.3. This means we have an element of order 4, so that gives us, of order 9. So that, if we call that A, then A to the third and A to the sixth are 2 elements of order 3. So we need to know, do we have any elements of order 3? So first, does square root 3 lie in this field? That's a prerequisite. It definitely should. Therefore, I ask 3 over 71. And now what was the law there? We have to take the modular with respect to 12. Now we have 72. So square root 3 lies. And I would like to know what is the square root of 3. And we'll just let Mabel do that. Oh yes, from And I need to go back and check what am I doing here. It's 71. Is that 13 times something? Oh no, it couldn't be. It must be a prime or a prime power. '73, 71. So it's 6. That's 216 minus 200. So that's 6. The next square roots we should check was 1 plus minus 2/3 times 6. So, do they lie in the field? And we can do that by explicit calculation. So that's true, that lies in it. And then 3 lies in it. So square root 6 should be in it as well. So that means we have a lot of valid x values. We'll just find those square roots. 2 and 6. 2 is 49. And 6 is 10. I just wondered if I could do it by putting 6 to a rather high power. I'm not really sure what it should be. 6 to 35. What? It's just the inverse. So let's try 17 instead. I'm just trying here. Yeah, I don't know what to do there. It would take a little while to find out, but never mind. Square root 6 was 10. So now we have 4 x values. For a total of 8 points, or 4 to 3, of course. Plus minus 10, plus minus 49. And we will then so either plus or minus, and not both, will be squares. So this guy gives 2 points, and this guy gives 2 points, to a total of 4 points. of order 3. So we have to go back to checking. If this was the case, we'd only have 2 points. So here we have 4 points of order 3. So this is my answer. And the very last one, 11 to the third. This is modulo 3, modulo 4, so this is as well. $1,332. Two, 3 square, both squared, 37. 2, 3, both squared times 37. So it's the same question again. 2.2.3.3.37 or 2.2.3 squared. It's just a question of finding out whether 3, of course 3 square root 3 should lie in this field, in this Galois field. So we just have to find it. I don't think we should make I don't think we need this. So we should find square root 3. Now what am I doing? It's that was not good. Covert. All right. If x squared equals 3, then print x. Five and 6. So it's actually in 11. Of course it is. 125, that's 5 to the third, minus 11 times 11. That gives, oh, surprise! It's still 4. If we do this in that's very weird. It appears now that I didn't put it in the third power. I only had to square it. That's 25 minus 22. There we go. So obviously, it's just 5. So it becomes quite simple. Now dividing by 3, we have to do that. And we need to divide it by 3, as far as I remember. Nine mod 11. Now if we take 3 times 9, that's 27. And divided by 22, that's 5. Oh, this is just 5, of course. And, silly me, if we subtract 22, we get minus 6. Divided by 3, that's 2. So it's the same as plus minus 2. Of course, so it gives square root 3 or square root minus 1. So does minus 1 lie in the Galois field? And this is a negative. It's 12 minus 1. So that was a no, but 3 does. So that gives us 2 x values plus minus square root 3. And then we get 2 values of y. Squared plus or minus something, and since minus 1 is not a square, the Jacobi index is minus 1. That means that one of them is a square, either the plus or the minus. So that means we get 2 points of order 3. Therefore, this is the right answer. Oopsie, 3 squared. I believe that was that. I had a nice cheese for lunch, Gruyere, which I like very much, with biscuits. So I was really strong doing the last part here.